Für diesen Vortrag spreche ich meistens in Englisch, aber ich will ein paar Wörter in Deutsch sagen. Viele meiner Vorfahren sind aus Deutschland gekommen zwischen 1850 und 1880, besonders aus Hannover und Marburg. Es gibt Namen wie Kieselbach und Bayerhofer und Aufenkamp und Mainzen in der Vergangenheit meiner Familie. Meine Herkunft ist also zum größten Teil Deutsch und Deutschland ist sehr wichtig für mich. Leider kann ich nicht sehr gut Deutsch sprechen. Aber ich kann versuchen, wenn Sie mit mir sehr langsam und sehr einfach sprechen. Auch meine Frau ist Deutsche, Claudia. Aber wenn wir in Frankfurt mit dem Flugzeug gelandet sind und auf die Autobahn fahren, mag sie es nicht, wenn ich sage, rum, rum, und jetzt bin ich Deutscher. Okay, back to English. Anyway, thank you again, the Joachim Herz Stiftung and University of Hamburg and the prize committee. Thank you for this tremendous honor. It's really exciting to be here and to have a chance to talk about this subject that I love so much. I've been properly embarrassed now by all the attention, so I'll just try to muddle through this talk. I think the main events we've already seen from the beautiful talks earlier today. Some of the subjects I wanted to at least mention briefly are to say a little bit about the background of the trilobite molecule discussion, which you may have already heard enough, about one of my other favorite projects about H3+ molecule, and a bit about our more recent interests in pushing 3-body and 4-body and even 5-body collisions at ultra-cold temperatures and into regimes that are not yet understood and are fascinating to me. So I do want to acknowledge that all of the work I've been doing, I didn't really appreciate this when I started out in physics, how social and an endeavor this topic is. Even theoretical physics, you kind of imagine a monk or someone sort of slaving away in a dark room, maybe with a computer and lots of paper and pencils on their own. But actually, it's a big social enterprise, interpersonal communication. And having worked with over 40 graduate students and postdocs over the years, in addition to so many other colleagues, has been a tremendous part of the excitement of this whole field for me. I should maybe just make one brief advertisement for a postdoc coming out onto the market soon, PhD about to finish, who is really excellent if you're interested in someone with our toolkit. She really embodies that. And I also need, of course, to pay a debt of gratitude to my advisors, Ugo Fano. He really taught me his way, his style of doing physics, and it really sank into me, I would say. And he steered me to my two postdoc mentors, Richard Zare at Stanford and Christian Jungen, who taught me molecular quantum defect theory. I should say I sprinkled a fair number of photos. Another thing I didn't realize about this field when I first started is how much you end up traveling, just like going everywhere in the world. So we've been to South Africa, Australia, Japan, and I've tossed in as mild entertainment a few samples from these. But in particular, this is just a kind of, this picture always reminded me of the intense days as a graduate student in Fano's group, where he would ask you at the end of the day at 6 o'clock before you went home how things were going, how were your research project, and then first thing you came in the morning, you'd say, well, what's new today? So kind of implying that there should have been a lot of work done in that 14-hour stretch since he last saw us. Just to briefly set the stage, we've already heard about what theorists do versus experimentalists. I have this kind of simplistic view of the subject, having worked a bit in both fields, experimentalists having wires and vacuum pumps and stuff. And there you see it, wires and vacuum pumps and stuff. I admire people who can control all these, make the electrons and the photons go where they want them, and do these incredible experiments with them. Theorists, well, we have our toolkit too. We need our water, coffee, paper, pencil, and computer, and, well, once in a while a telephone before the days of Skype. So our microscope, in a sense, for the theorist in this field is the Schrödinger equation, or if you're doing relativity things, possibly the Dirac equation. And this is our window into the atomic world that we're trying to use to understand what is the nature of this intriguing partial differential equation, which in many different contexts we know really describes so beautifully, so accurately atomic phenomena. And so a lot of this field is developing the math and the computer methods to solve equations like this. But not only that, it's also, and this was one of the things Fano really stressed, is building intuition is so key. Almost all the problems are not really by brute force directly solvable, as in the sense of just sort of, make the computer give me the exact solution. Most of the problems we're working on, they're just too complicated for that. And so we need to hone our intuition to build our ability to see sort of what's kind of going on here, and, well, what's the electron sort of doing there, and try to see what are the qualitative things going on. And in some cases, we also kind of pay attention to experiments, but also it's important not to obey them, okay? If they say, the experiment says such and such happens, well, sometimes that's not actually true, and then in some cases the theory is actually useful in clarifying those points. So one of the qualitative problems of this field is that in the Schrödinger equation, because it depends on every variable of the system, this quickly explodes as you add just a few particles. You add more than a handful, 2 or 3 particles, you've got too many coordinates depending simultaneously interacting with each other to really solve this. And quickly the problem grows exponentially. So this honing of intuition is especially important. And one of the things that I picked up from Ugo Fano, I think it was when Charles Clark and I had done kind of a secret project that Fano didn't completely approve of, and we were going to submit a paper to the 1979 Kyoto ICPEAK meeting. And Fano, well, he ended up condoning this, and we said, okay, you can go publish that paper on 3-electron hyperspherical. Go ahead and send in this abstract to Kyoto where you make these predictions that you've written in your abstract, and you're kind of sticking your neck out, And he said, well, don't be afraid to stick your neck out, but just remember it might get chopped off. And we followed this metaphor a little further. In fact, that abstract we sent to the 1979 Kyoto ICPEAK had a completely incorrect interpretation. Anyway, it was survivable for me, but just barely. But we do try to keep that in mind, and we do try to stick our neck out from time to time and go to the boundaries beyond what is really understood, and realize that in a lot of cases we're going to have the chance of being wrong. But someone once told me, if you're not wrong once in a while, then you're not working on problems that are hard enough. So these are a few of my favorite projects that I wanted to mention a little bit about today. One, which was a case where we stuck out our necks with this H problem, where you try to see, are there states where you could actually temporarily trap three electrons near a proton, 2 electrons in addition to the hydrogen atom. This was one that intrigued me a lot because there was both experiment and theory that said these quantum states existed. But for the life of me, I couldn't get any intuition about why this would be so. And so there was a 10-year project that culminated with some work Francis Robichaud did when he was in my group, where we made the first, at least for me, anti-prediction in the sense that we ended up doing detailed calculations that seemed to be saying, and we couldn't escape it, that the experiment had to be wrong and the theory had to be wrong. That said these, even though these were apparently in agreement with each other. Another of my favorite problems is H3+ dissociative recombination, where there was a rather different story. There was experimental evidence about the recombination rate, but theory could not come within orders of magnitude of getting the correct rate. And so we had to really dive deep and forge together different elements of our toolkit that had never really been connected before and able to solve that problem. You've already heard about the trilobite Rydberg molecules. And then more recently, I've been pushing on quite a bit for a decade or more about FMOV resonances, universal physics in the limit of large scattering lengths in ultra-cold gas. So let's talk briefly about the ultra-cold Rydberg molecules. I know you've heard about this quite a bit. And again, this started as a pure curiosity problem, that we had seen that others, notably Françoise Massenou in France, had been applying this Fermi method to try to study some of the simple excited states of molecules, and was showing evidence that it was kind of working and telling non-trivial things about the molecules that otherwise are very hard to predict using quantum chemistry codes and so on. So we thought we would explore this method too, see if we could maybe improve it, make it into a more quantitative tool. And in the end, then, once we reached a point of understanding it, see if it could be pushed into new regimes that had never been explored before. So that was more or less the motivation. I call this I'm trying to get the chemists to accept this term, that this is now going to be sheepdog binding, because, but so far it hasn't really caught on, because I kind of think of this Rydberg electron as kind of a sheepdog that makes a little tug and keeps the atom in tow. It keeps coming by and adding a little attraction, then it goes away, and then coming back and add a little more attraction, and in the end it's stuck there for long periods of time, and people like Tillman Fowler are able to see it in the experiments. So anyway, there's the sheepdog, and that's that silly metaphor. So the PhD student who I was working with in the 80s, who we were exploring this with, was Ningyi Du, and we thought this was kind of a funny-looking potential curves that we were getting out, these oscillating potential curves. I'd never seen anything like that. Potential curves between atoms, everybody knows, you learn this, they simply go down and they come back up. They have one minimum and they're very simple, and the molecule, the nuclei vibrate in the minimum of the potential. So anyway, we called this kind of a funny thing that we had noticed, and I think I was interviewed after this prize was announced by some reporter, and then a few weeks later I started seeing odd descriptions appearing online. In particular, there was this strange story titled "Purdue Highbrow Receives Hamburg Prize," and I was quoted as saying, "We saw some unequivocally humorous wiggling force fields between A atoms that unequivocally astounded us. Even in the late 80s, we and my tyro were perplexing to figure out if this could indeed be observable." I don't think I really said it quite that way, but sometimes these things get scrambled in translation. These are the wiggling force fields that were so unequivocally humorous. Yeah, we were intrigued, and at that time we were trying to go around to experimentalists saying, I mean, surely there must be some amazing things in the spectroscopy of these. Why aren't you looking at these? And experimentalists would look at me and sadly shake their head. Silly boy, suggesting these crazy, impossible experiments. Later we found there are other papers that, well, in the 90s, for instance, there were papers you could find in quantum chemistry publications, seen also these sort of oscillating potential curves. And about the same time as our work, there was an important paper, almost the same physics we had seen of Eugène de Prunelli in Saclay. So I was starting to get a lot of confidence in all this, but then when there was zero experimental interest at the time, I pretty much left that in the 80s and didn't think about it again until the late 90s, when now the whole scene had changed because ultra-cold atoms were there, Bose condensation. You could make heavy atoms have these Rydberg states and make them very cold. And it occurred to us that we could turn these humorously wiggling force fields to perhaps actually make bound states in these oscillating potentials. And this project with Hossein, which came during a sabbatical year, those are the times when academics really have time to think. That was the case that year. We could think about sort of whole new directions. And we worked out the implications, and that led to the paper that's been quoted today and was cited in the prize this year. And so we saw graphs like this. This was actually the 30D 3/2 state. Tillman was talking about D states earlier, but he wants to apply a magnetic field and screws all this up. That wasn't very nice. But he has another way of seeing really neat physics in this same system. And and you see the bound energy levels where the nuclei are really stuck, vibrating out at this large distance of 1,500 Bohr radii. And then there's this other graph that you saw with its quantum states near the bottom of the well and all of its interesting physics that came out of that you've heard about. And then one night, working late in Jilla, I decided to plot these, and I was amazed. The molecules looked like this. No, that's the wrong picture. No. This was a baboon that was aggressive, had taken a sandwich away from a colleague during a tour in South Africa a couple of years ago. But yeah, it looked like this, and of course it struck me immediately that this resembled a trilobite. I don't fully agree that it was my secretary who coined this term, but I'll have a talk with her about that, spreading these rumors. Anyway, yeah, here's the rubidium plus ion, here's the electron cloud, and it's been a lot of fun looking into the properties of these systems and then actually seeing them realized. Now, the way I found out that you can really tell when you're famous, it's when your work is featured in a magazine that has naked people on it. That's one way to figure out whether it's important or not. And there was a story in this fine German publication that featured it and has this quote, gehen viele Grünmuster in der Natur auf Quantentelepathie zurück. Okay, I hadn't made this connection with quantum telepathy, but it's interesting to have it pointed out to me. Anyway, yeah, we were still worried about sticking our neck out in the trilobite molecules, especially when this appeared on a textbook cover, but we didn't really know, was this really a fundamentally flawed theory or not? And, well, for Peter Schmelzer, if it were I would have to go down the toilet. But in the end, it didn't have to be because of Tillman's great work. And we were also kind of disappointed after we predicted another class of molecules, butterfly Rydberg-Molecules, that there were all these bumps and things. You couldn't really see the nature of the wave function well enough. So again, in a fit of what John Bone was talking about, my fascination with Pavre and graphics and trying to understand if you could really help you to understand the science, I made this flyover of a butterfly Rydberg molecule. Oops, it went away. Which helps you to see the details. Okay, I don't know about you, but I learned a lot from that. Okay, so then there came the experiments, and it all worked beautifully, and you can actually see in the spectroscopy these levels we predicted and these annoying levels we didn't predict, which have now been understood. And that's all I wanted to say about the Rydberg molecules. Let's see, well, how is the time coming? Okay, still plenty of time. Okay, so now let me shift gears to this H3 plus problem, which is actually of some practical importance because there is a need to understand how much of this funny, the simplest triatomic molecule ion is out there in interstellar clouds because it collides with almost any neutral molecule and dumps a proton on it. So if you see carbon atoms there, this will make CH+. If you see oxygen, it'll make OH+. If it sees OH, it'll collide and it'll make very efficiently H2O+. Okay, so this is the root. This molecule is actually crucial in seeing how water can get formed in these interstellar clouds. And there are spectroscopic signatures where this molecule has been seen and it's known to be there. And astronomers, especially the ones doing chemical astrophysics, were struggling to understand exactly how much H3 plus was there. It was known how it was formed by protons triggering reactions and so on, but the destruction rate was almost completely unknown, and the few experiments that existed seemed to be in conflict with both theory and with the astrophysical observations. So we had to, just to make a short version of this whole story, we had to invent with Slava Kokolin back around 1999, we started thinking about this problem, which I had never really worked in this field at all before. And basically the idea was to incorporate new physics that had never been put into the electron collision with this ion. Such as the Jahn-Teller effect. This was usually thought to be a spectroscopic kind of effect discovered by Edward Teller and his co-worker back in the 1940s. And it wasn't really thought normally to be a player in an electron collision process. But when we put this in and we did the rest of kind of welded together the rest of our toolkit and did around a year worth of computer time, we found, in fact, we could get a pretty satisfactory solution to this problem, which gives the overall dissociative recombination rate as a function of energy over this whole scale, whereas really before this work, the best theory was about 2 to 3 orders of magnitude below this. So this really taught us a lot in how to extend our methods into new regimes. We had never tried to do that before. One thing that was interesting about this is that we couldn't get this good of an agreement unless we assumed a much higher temperature than the experimentalists had told us they thought was relevant to the ions in their beam. I think they thought it was below 100 Kelvin, and we assumed for this graph around 1,000 Kelvin in order to get this level agreement. And it was distinctly poor agreement if we really used the experimental temperature that had been quoted. And later it was a publication by the experimental group showed that in fact there were systematic effects that had not been understood well at this time, and the temperature was a factor of 5 to to 6 times higher than originally quoted. And so, in a sense, I think our theory helped to understand the experiment better in that sense as well. One of the other things that, of course, we like to do is not just account for experimental data that's out there, but we saw all sorts of resonances in the spectrum, and we wanted the experimentalists to find them. And so, again, Slava Kokolin and I were recommending for years experimentalists try to improve their resolution and be able to resolve some of these individual resonances. And that led to this collaborative paper with the group of Andreas Wolf in Heidelberg. This whole project came out of my sabbatical time there on the Humboldt Award, where you can start to see there are actually a lot of substructures that are beginning to resemble the experimental data, and that they are really beginning to see some of the resonance features that we had been predicting. On the other hand, when you go to lower energies than this, below 50 millieV, it looks like there's almost no correlation between our predicted resonance spectrum and experiment. And so there's probably a problem with the theory here, although it's not ruled out that maybe there's a problem with the experiment in this very low energy range. Now I kind of wanted to talk a little about some things that go really back to my PhD thesis work, again with Ugo Fano, where he was promoting a view of all collisions, electrons or atoms, heavy particles, light particles, as being describable as a single coordinate of the system, a single collective coordinate as being the major player, that you could map everything in this many-dimensional space onto just one coordinate changing. And this idea intrigued me that a complicated chemical reaction or nuclear reaction like A plus BC plus D could be viewed as one coordinate, this hyperradius coming to 0, and then going back out to large distances and breaking up, fragmenting the system in some other way. And in this sense, he was promoting this view that all reactive processes could be mapped into this picture. But at that time, it was really very impractical and very, very hard to do any calculations like that. Nevertheless, I think it gave some nice insights and basically allowed you to take the intuition you get from chemistry, we kind of all get this in our first quantum classes, how to look at a potential and think of how motion in that one coordinate behaves. And carrying that over to many particle dynamics, it's a real challenge, but it also has resulted in a lot of intuitive results and quantitative results. So this was kind of the elements of Fano's vision, that he was always promoting the idea that you should always look at the eigenmodes. This is a great word, this German word eigen. The modes really of the system, intrinsic to the system, are what really matter. And you can think of diagonalizing a Hamiltonian or other of the quantum operators that are relevant to any given process in nature. And he really suggested this, and this whole hyperspherical viewpoint, which lends naturally into semi-classical ideas like Landau-Zener, WKB, things like that, kind of took us into the land of understanding three-body recombination, like 3 helium atoms simultaneously colliding, forming a helium dimer in an atom, these kind of processes that go on all the time in Bose-Einstein condensates. And so just as a little history, I still remember the day I joined Fano's group at Chicago, and he had given me this paper, actually even before I joined the group, and wanted me to read it. Had all these equations, and this all really looked cool and completely ununderstandable. All this math and going to weird coordinates, hyperangles, hyperradius. But anyway, he ended up giving me this as a thesis problem to basically try to generalize these ideas for the alkaline earth atoms, which Masek and Chi-Dong Lin had developed for the helium atom. It seemed like a fascinating but very hard problem, and I soon got tired of trying to do what Fano told me. and sort of had to reinvent the problem into just calculating the doubly excited states of beryllium this way. And in the end, I think I conclusively showed that this was the most inefficient method ever designed to calculate autoionizing states of the beryllium atom. So I learned something from that. We all learn from our projects. But one of the things that kind of came out as we kept pushing these methods, in particular when Francis Robichaud was in the group, we tried hyperspherical, we tried configuration interaction methods, we tried some ideas from basic scattering theory, and in the end, we made this anti-prediction. We found 3 different ways that all seemed consistently to say there could not be a doublet p-odd resonance of the hydrogen doubly charged negative ion. We could not find any sign of it. So finally, we wrote this paper, which I'm rather proud of, because we claim the theory was wrong, that said the experiment was right, and of course the experiment was wrong. It was only a couple of years later, well, maybe 1 year later, that Lars Andersson at Aarhus came up with this measurement showing the dark curves, the dark dots were his new data over the energy range that had claimed to see this doublet p-odd resonance. I think it was called 2s squared 2p resonance of H double minus, showing that, in fact, it didn't. Although, on the other hand, you might say this didn't really solve the problem, because now you have one experiment that says there's a resonance, one theory that says there's a resonance, one theory that says there's not a resonance, and one experiment that says there's not a resonance. But later, this experiment was repeated in Japan and confirmed the Aarhus result. So we're pretty certain now that there is no resonance, that hydrogen atom cannot bind even temporarily 2 extra electrons, at least for this symmetry. But that was one case where I really thought we were sticking our neck out, because it really did seem like we were disagreeing with a lot of solid, good physicists with good reputations. Okay, so now let's move on and let me say a few things about ultra-cold atoms, which has been a major focus in the last 10, 15 years. So some of the things that came out of our work in this area are the fact that really for this system, it turned out that all that what felt like wasted investment in the hyperspherical method back in my graduate school days in a very inefficient method, it turned out to work much better when you do neutral atom collisions. And using this, we've been able to understand a lot about 3-body, 4-body recombination, even 5 bodies that had never really, the other techniques simply were not able to predict. And all of these connect with universal Efimov physics. So I'll say a few words about now. So, of course, you all know what a Bose-Einstein condensate is, cooling down a gas. And it changes from a thermal gas finally to this one quantum state for all the atoms. But while the experimentalists were very clever in turning off all the bad 2-body collisions, finding just the right states and magnetic traps that rotate or do something to plug the holes in the trap, all that cleverness could not turn off the bad 3-body collisions that were causing atoms to be lost from the trap on about a sort of a few second, 1 to a few second time scale. But really there was almost no ability to calculate the rate of 3 bodies simultaneously coming together in the condensate and forming a diatomic molecule and an atom and releasing all that energy that ejects all 3 atoms then from the traps, from the condensate. So with a really bright graduate student, Brett Esri, and another one, Jim Burke, we tackled this problem and tried to apply this hyperspherical toolkit to this problem. And basically, it took a long time, but finally we were able to start getting stable results. I still remember that I was kind of getting really pessimistic that this would ever work. And, I give Brett and Jim Burke a lot of credit because they they just came in my office and said, let's just calculate it. Forget all this theory stuff. Let's just calculate it and see if it's stable, if the calculations are reliable and don't change with respect to all the parameters in the calculation. And sure enough, they did it and found we could get very stable results. These are actually, these different dot colors and so on are different Hamiltonians, different calculations, and they always seem to be showing a universal phenomenon in the three-body recombination rate as a function of the two-body scattering length. And we found then, by digging in deeper, much as we were sticking our necks out, it sure looked like the theory was going to give an infinite number of resonances. And those resonances had Efimov character. This bizarre Efimov effect, which had never been observed experimentally, appeared to be observable in this system. And it also showed what I thought was the most important observation, was that the three-body rate appears to turn off at some magic values of the atom-atom scattering length due to a quantum interference effect. And there are predicted to be an infinite number of such minima, again, in a connection with Efimov physics. So again, there was really no experiment whatsoever in this field at that time when we stuck our necks out with this prediction. And it took till about 2006 that there was this impressive experiment in Innsbruck that could see three-body loss in a cesium gas and could see this first resonance we predicted, which looked very much like the one we had said should be there. You can't really see the sign of a minimum on here, but actually if you blow it up, there is a minimum that you can see, which seems to possibly have something to do with this prediction of a minimum we saw, although on this logarithmic kind of scale, you can't really see it on this graph. But this seemed to suggest that all this math we had done and calculation was working, and we could have some confidence in it. And later, the fact that there are multiple minima and multiple Efimov resonances was confirmed experimentally as well, some other aspects of those predictions. But then around that time, after the Innsbruck experiment, it started to feel like three-body Efimov physics universal interactions at large scattering length was beginning to be pretty well understood. And so we decided to try to see, can you push these methods? This developed some understanding about four-body collisions. Kind of my rule of thumb is each extra dimension in a partial differential equation adds about an order of magnitude of difficulty to the problem. So in that sense, we estimated that probably this four-body problem for bosonic atoms would be around 1,000 times harder probably than the three-body problem. And so in fact, I deviated from my usual sort of modus operandi at that time. I usually had like one student working with me on each student or postdoc working on a different project. Well, actually, for this four-body problem, we had about four people in my group: Nirav Mehta, Seth Rittenhouse, Javier von Stecker, working with me. Someone else I think I've forgotten, and spending a good fraction of their time working on this problem. And the early days were rather grim because progress was really quite slow. But in the end, thanks to a particularly important insight by Javier von Stecker, how to add one new element to our toolkit, which was using correlated Gaussians to get the hyperspherical potential curves, we found we could, in fact, get hyperspherical potential curves for four interacting bosons. And they had this interesting property that each four-body curve converges to an Efimov state of the three-body system at infinity. And it predicted that, for instance, there should be two four-body resonances attached to every Efimov resonance. So again, we stuck our neck out there. There had been other theoretical work also by Hans Hammer suggesting also something like this. But one thing we were able to do was actually push this to the quantitative level of really doing a four-body recombination calculation. So in this hyperspherical picture, you come in on a continuum state of four atoms, four free atoms, like in a BEC, and they have some non-adiabatic physics and can go out into dimer plus dimer channels or trimer plus atom channels. Classically, you can be kind of thinking this is roughly what happens here. Four atoms coming together, simultaneously exchanging energy and releasing then that energy in the form of kinetic energy of the fragments formed. This experiment, I would say it was later done and confirmed our prediction, but actually it turned out the experiment had been done before our prediction. This is actually data from the three-body loss paper of the Innsbruck group, which had already seen this resonance, but they didn't really realize at that time it was one of these universal four-body resonances. And so this was the main story, that we could predict the scattering lengths where these two resonances appear. These have since been confirmed, and again adds to our confidence that we understand really the basic physics of this system and can interpret it quantitatively. So, well, we're ambitious. Why stop at 4? Okay, so we did make a stab, actually seeing that, and this is mostly Javier von Stecker's recognition, that these universal resonances form a family. There should be 5-body resonances that can show up in recombination. There should be a point where losses are dominated by 5 atoms simultaneously coming together. It's normally thought that 3 coming together in a cold gas is a relatively rare process. But even 5, for that to be the dominant resonant process in losses of a quantum gas, this seems hard to imagine. But this is what the theory seemed to be pointing to. And we did collaborate with the Innsbruck group in a real tour de force. They were actually able to measure recombination and see the 4-body loss that we had predicted before, in which they had measured previously, and with an extra little bump, which couldn't be explained if you just used 3-body and 4-body recombination theory. But if you put in 5-body recombination resonance where it is, it's right there where it's expected, and its magnitude, I think it was off by a factor of 15 or so from the predicted magnitude of this cross-section. But in sort of ordinary SI units, this number is something like 10 to the minus 100 centimeters to the 9th per second, or something like that. And so I always say, you know, what's an order of magnitude among friends? So, as John said, I got kind of carried away with these graphical metaphors: the trilobite molecule, the butterfly molecule, cavorting cobras, the peanut and mushroom. This, I couldn't think of an animal, so it ended up being firestone radials. Well, that followed up some of my early work with Pavre on double condensates, where my students were always intrigued that I put a robot in this picture, and to this day I don't remember why. So anyway, I think if there's a take-home message from all of this, one is at least that I think it's worth following your vision, your image, your intuition, and that sometimes means following an unconventional approach which differs from what everyone else is doing in the field, and often this leads to dead ends, and you realize that all these people working in the field actually were doing a pretty smart thing. But every now and then, I think Feynman realized that too. Having a completely orthogonal way of approaching some classes of problems compared to the normal accepted ways does pay dividends. And some of the methods which have really many times seemed very unpopular and not used much in the field, like hyperspherical methods, multi-channel quantum defect theory, the frame transformation. Sometimes I feel like we're the lone beacons in the wilderness using these methods, but they have actually paid dividends in a number of problems. And I think it's important as theorists, that, as well as experimentalists, but I'm thinking from a theory point of view, it's important to stick your neck out, to push make predictions, to try to see where the field can go and where our understanding might take us. So thanks for listening.